In February 2026, data from Imperial College confirmed a structural tipping point for the internet. Automated and AI traffic officially exceeded human traffic. To understand why this creates a crisis for internet service providers, we have to establish the historical baseline. From 2017 to 2022, global IP traffic reliably doubled every 18 to 24 months, driven almost entirely by humans streaming video. Because humans consume far more data than they produce, physical network infrastructure allocated capacity at a roughly 10-to-1 downstream to upstream ratio. In standard DOCSIS spectrum allocation, this physical limitation becomes visible. Only the narrow 5 to 42 MHz band is reserved for the return path. ISPs engineered these networks over decades to deliver passive consumption. That architecture is now colliding with an active, machine-driven user base that generates massive outbound data. While a typical human internet session requires about 75% downstream capacity, AI workloads invert the model. Web crawlers and model training synchronizations frequently demand 70 to 95% upstream capacity. This pressure comes from several overlapping sources: continuous analysis from smart home cameras, federated learning models updating global networks, and autonomous agents syncing code repositories. 24 hours a day, all require heavy outbound data. As a result, the required symmetry ratio of the network is rapidly compressing. Heavy users are shifting the 10-to-1 average toward 3-to-1, and in some cases, approaching a strict 1-to-1 ratio. An ISP can deploy massive 10-gigabit downstream links to a neighborhood, but users will still experience severe lag and buffering. The physical bottleneck has silently shifted to the return path. To see exactly how upstream saturation destroys downstream performance, we can look at data collected by AppLogic on Tesla's full self-driving training uploads. When these vehicles connect to a residential Wi-Fi network, they immediately begin uploading sensor data. This triggers a sustained 100 megabit per second upload that lasts for more than 10 minutes, completely monopolizing the local node. When AI data saturates the upstream queue, it jams outgoing requests. TCP acknowledgement packets become a critical failure point. Trapped behind massive machine uploads, the feedback loop breaks. The server assumes a dropped connection, halting downstream video entirely. To keep these feedback loops functioning, network operators must deploy deep packet observability and quality of service shaping to prioritize vital ACK packets over bulk machine uploads. Saturation in the return path breaks the basic mechanics of data delivery, throttling downstream throughput regardless of how much capacity is available. This structural failure extends past the physical cables and into the logical routing layer. For decades, ISPs handled massive video traffic by relying on content delivery networks, or CDNs, which cache static files close to the end user. AI-generated content breaks this model. An AI response is highly dynamic, unique to the individual query, and impossible to cache. Requesting a popular movie creates a short routing path, terminating at a localized ISP edge server. But an AI query bypasses this edge cache entirely, forcing a complex, multi-hop route all the way back to a centralized hyperscaler data center. This bypass renders billions of dollars in edge caching investments useless for AI workloads. Massive, unpredictable traffic flows are now dumping directly onto expensive core transit and peering links. The shift to machine-generated traffic also dismantles how ISPs plan for daily capacity, a model historically based on human sleep schedules. Historically, networks saw a massive downstream peak in the evening and a quiet early morning valley, but AI agents don't sleep. By 2028, automated upstream traffic will completely fill this morning valley, flattening the entire 24-hour baseline. Within a few years, overnight hours will generate upstream volumes that equal the historical primetime downstream peaks of 2024. The quiet hours that operators relied on for network maintenance are disappearing. Access networks must now be re-engineered to sustain near-constant, heavy bidirectional loads around the clock. To see how network operators can survive these constraints, we can look at multi-orbit satellite networks, which operate under extreme physical capacity limits. In a low Earth orbit constellation, satellites move rapidly across the sky. When a terminal hands over its connection from one satellite to the next, the network experiences severe, temporary capacity drops. These AppLogic wave graphs compare satellite handovers. Left, no shaping, lets AI traffic consume scarce bandwidth, crushing jitter-sensitive video calls. Right, with shaping, automatically throttles background traffic during capacity drops, protecting the real-time session. Terrestrial networks are beginning to face the same upstream constraints. Without deep packet observability and active shaping, fragile real-time human applications will collapse under the weight of background machine noise. Surviving this transition requires significant capital expenditure. The asymmetric network architecture is reaching its operational limits. Current DOCSIS upgrades, such as mid-split frequency expansions, offer a temporary bridge. They provide enough upstream relief for today, but fall short of the continuous demands created by agentic workflows. This table compares symmetry ratios across broadband technologies. Legacy DOCSIS 3.0 operates at 5:1, while DOCSIS 4.0 FDD improves to 1.7:1. The ultimate destination is fiber to the home. Technologies like XGS-PON are naturally symmetric, delivering a strict 1:1 ratio with virtually unlimited capacity. Deploying fiber and high-split architectures provides the physical capacity required to handle continuous outbound loads without compromising service. Upgrading the physical layer is only half the solution. Managing the logical layer requires a completely new approach because static capacity forecasting cannot anticipate unpredictable, bursty AI traffic. Network operators are turning to network intelligence. This uses machine learning models to forecast traffic growth on a node-by-node basis, allowing the system to dynamically allocate spectrum precisely where it is needed. Automated anomaly detection and real-time quality of service shaping at the edge will serve as the primary defense against sudden, localized upstream exhaustion. Rather than waiting for engineers, an autonomous network node instantly analyzes incoming data streams, categorizes packets, and throttles non-essential background noise in real time. Future network operations depend on moving away from static bandwidth allocation towards self-optimizing systems that prioritize human interaction within a constant stream of autonomous data.